They are the most important part in understanding the functionality of any transformer models. So whenever you see any word like embedding tokens, what is happening? Like if you can see from this diagram, this is the sequence of inputs and it is getting mapped to a vector. So this mapping, which is something very important for transformers, and this is something which is called the input IDs that we are doing here. And before this ever gets used for any transformer model, it is going to be added with the positional embedding. So if you can see what is happening here, this is your token embedding and this is your positional embedding. You are going to take one vector from here, from left and right, and do the addition, and that's how you form the tokens from there to embedding. So token is just a single number, whereas the embedding is a two-dimensional array. You can say you can. So it has the C column and C rows and T columns. So this also depends upon the size of your embedding and the number of tokens that has been presented. So now let's see what we have done till now. We have done our installation and we have loaded. In the previous session you have seen how to load a model, and through the with the help of pipeline we have run a simple text generation pipeline. So now we don't want that. We are not going to do always that easier. We are going to deep dive and look inside what is happening. So let's go to the stage where we can see these things, like from this English word, how the tokens are being getting generated. Let's see them. So let's for that will be done with the tokenizer. So I am actually loading the model again just in case, so you can ignore it, just to so that it saves our time. Yeah, now so from tokenizer we'll pass this prompt: write an email for tragic gendering mishaps, explain how it happens, and this is the assistant tag, which means after this tag the generation should start. So we pass our prompt and then we ask to return the tensors. PyTorch tensor dot input IDs to CUDA. So you need to, so this input ID generation happens at the CPU, so we'll need to send them to our GPU. Here you can see these are the mapping of these tokens. This maps, some word maps to 14350 and like that. So now let's see how the words are getting generated from the model. So for that generation, so we'll call model dot generate, and we can pass, there you have to pass the input IDs. It's not model directly don't take the word, instead it takes the input IDs. And let's see if the generation is successful. Perfect, it is generating the output for us. And let's do one thing, let's ask our tokenizer to decode the generated output. So let's print tokenizer dot decode generated output. Yeah, so although Google Colabs does that for us, but this is how it's done. This used to be the prior version of Transformer, but right now the current version of Transformer handles pretty much all of it. So now I'm actually more interested in the in seeing the how does the tokenizer is actually tokenizing our input sentences. So let's do iterate in for the input IDs. Let's see what are these things meant actually. Like 14350 maps to what English word. This is something that I wanted to understand. So for that you can go decode and you can pass the ID. Perfect. So see, now the mapping is like this, and if you can see the tragic has been splitted as track and IC. So this is something the tokenizer responsibility is to do that. And you can like from what now what I wanted you to show, how can you compare how can we compare the trained LLM tokenizer. So from transformers Let's import. I think we have done importation. So like it would be better if you can see them as the color list of how things are being generated. So I have made one helper function which exactly when you pass them the model, based on what model, how the tokenizer is working. So this function is just mapping the colors based on how tokenization is done. So I have one prompt. Let's see. This prompt has everything like emoji, capital letters, and expression, mathematical expression, and all. So let's see how uh, with the help of this show token function will it be able to show us how the splitting of tokens occurs. And let's do it. We can pass this, and let's look at the BERT models, how their tokenizer does the tokenization of this word. I believe it's the spelling issue. BERT base. Oh, sorry, it's un. Yeah, so it's bringing the BERT tokenizer, and see how the tokenization is starting. Start with CLS, then English and capital. Then it's breaking capitalization as ijation hash hash, and then next line as UNK show token false none. So show token false. So it has pretty much ignored this emoji. So I believe this model won't be able to perform well on such given languages as well. So this is a foreign language, so it was not able to tokenize it. And if you can see how it has tokenized every word from numbers into decimals, expressions as differently. So to compare this, let's bring GPT-2 tokenizer and see, because I just wanted to bring first a simple model, so that once we bring a difficult, I would say a more capable model, it should do a better. Perfect. Here you can see now it has respected the formatting. So GPT-2 is quite better model. And let's see one more example. So you can play with different models, how they are doing the tokenization to understand this. So let's bring Google's one of the model, Google Flan T5. Let's see, that would be interesting to watch. Yeah, so it's not that good compared to GPT-2. The tokenization, I won't say, but here it makes much more sense how the tokenization has been done. And you can try a lot of others, any models. So let's take this tokenizer from our model that we are using previously, Microsoft Y3, and let's go there and let's run it. It should also, it's also doing as good as GPT-2, which makes sense. So this is a good exercise in learning how under the hood tokenizer itself is working. Now, so this is how you done the splitting. How will you do the contextualization of this? I mean, the contextualization. How will you contextualize the word embedding for a language model? Like let's say smaller model. Let's take an example, bird. So for that, let's do one thing. Let's bring the Delta base model, and let's see the output shapes in terms of tensor, like what is the tensor size, output vectors, how does they look. And this will give us more idea, like because understanding the dimension is very important when learning the transformer or the PyTorch. Import auto model, and let's bring the auto tokenizer this time, and tokenizer Microsoft database, and let's also load the model. So from auto model dot from pre-trained, and then it's the same thing till Microsoft. The model we can change Delta V3X small, I believe. And let's do one thing. Let's get some tokens. So in the tokenizer, let's pass the word that we want to tokenize. Hi, you. And let's return the tensor. And let's also collect the output. Let's expand the tokens. Perfect. So it's bringing the model. The model isn't that big. I believe it should be done very quickly. And once it's done, so we are what I'm interested in first, seeing the output shape. What is the dimension? So I believe this is done. So dot, how do you see the output as dot shape? And so it's giving us the tensor. This is the dimension, and the 384 is the, I believe, size of the embedding, and 6124. So I believe it has broken that into 6 tokens, and this is the dimension. Let's see. Let's actually see. No, I believe it's from the output. So let's do one thing. Let's debug it and let's go inside the tokens. ID is 0, and let's print, because we just learned above how tokenize dot decode. Sorry, it's 4. Yeah, so it has broken that as how are you, and I think it is 4 sentences, and the CLS and separator it is counting, so that's how it becomes 6. Perfect. Now let's see the output. So it's a tensor, and I believe this is going to be 318 dimensions, and 1 2 3 4 5 6. Perfect. So that's something we saw it from the shape, and you can literally just see it if you're interested, like what are the tensors value. So that's also present. Now this is for uh, like, now let's understand the text embedding for sentences and also for whole documents. So let's bring the sentence transformer. Sentence trans. Let's import sentence, and then let's bring a sentence transformer. Transformer all net mpnet base v2. So they are useful in doing the text embeddings, and we can convert. This is a text to text embedding model, so we can extract the vector from this. You pass them plain text, and you get back the vectors. So let's see. It's hi how. So it's bringing the model. It's about 438 MBs, and I think we have now the vectors. So let's see the shape. So 764 vectors. It has created the embedding of that much length, which is kind of cool. And there is also one library which is called Gensim. There we can do the word embedding beyond the LLMs. So I'll also show you how can you do that. So from Gensim as API, and let's API dot load. Let's bring the Glove model. Glove wiki Kika world 50. So I believe GenSim, no module named GenSim. Let's install it. Now we should be fine. So here, what I wanted to show you is how the words are related in the embedding space. So let's say if we say the word uh, laptop, then what are the similar spaces word in that model? And for that, let's call model most similar, and we can pass model as, let's pass the AI. Let's see what we get back and how many. Let's get top 10 to be fine, I believe. So once it is done with what are the similar word related to AI, and let's see. All right, AI is not present. So let's use the word car because it's a very old model. So car is pretty much related to truck, cars, vehicle, driver, driving, bus, vehicle, parked, and motorcycle. So in the order of the similarity. So that's kind of cool. Like, and you can make even. So this is the example of the word embedding. Similar way, you can have the voice embedding as well, and you can also have the word to vec model bring, and that performs the most similar. This same thing from Gensing. What you have to do? So let me show you from. If your task is to do the similarity on the embedding, so there is one model also called word to vec, and you can bring that, and that model. So let's bring what models to bring, and then for this one you actually need to pass this a list of uh, f- a list of vectors such so that it can do perform the embedding. For now, I'll leave this as an maybe an assignment for you all to try on because I really wanted to uh, sh- go over to the next step, and we can look onto the next use cases of how can you build uh, like looking more deeper inside into the language model architecture with the help of PyTorch. So in the next video, we are going to see the input and output of a trained transformer model, their architecture, how can you see what layers they are using, and like the decoding methods, probabilistic distribution, sampling, decoding, a lot of more thing. And one of the most important thing is the key value caching for faster generation. So thank you for watching this session.